Hi, everyone. I'm meteorologist Eric Weglars, and with COVID-19 impacting so many of our lives, especially for those in school, I figured that I would join both Haley and Kevin in doing some of their weather lessons and create a few of my own that I think many of you will probably really get a lot out of here. And given that so much of meteorology is dense, it's tough to fit into a 3-minute weather segment. I figured that I would go through some of these more dense topics, show you what we deal with on a daily basis, and of course, broaden your horizons as to just how complex meteorology can be. So, welcome to On Cloud Nine. That's what I'll be naming my segments, a play on the phrase there. And the first segment that I figured I would do with everybody here will be an introduction to weather forecasting and weather modeling, which is also known as numerical weather prediction. So, as a broad overview, I will hopefully attempt to demystify some of the more complex portions of your favorite weather topics, which might include severe weather, winter weather, weather forecasting, things like that. And a number of these topics, like I mentioned, are dense. So I recommend that these lessons are, viewed by high school students and higher, especially those thinking of going to school for meteorology. They have a passion for all things weather, and maybe you're looking to add to your already well-rounded science background, then these courses will certainly be for you. I am the newest meteorologist here at WMUR TV in Manchester, New Hampshire, and like so many meteorologists, our passion for weather started with a particular event or series of events. Mine happened to be a severe thunderstorm when I was, I think, 9 or 10. So, boy, do I feel old. But way, way back when I was young, I saw the most vivid thunderstorm I've ever seen, and that really fueled my passion to where I am now. I also hail from Connecticut, which arguably features some of the most diverse weather across all of the Northeast. We have severe weather, winter weather, we have nor'easters, blizzards, we have extreme heat, extreme cold, we have flash floods, you name it, we have it. And that really was the catalyst for where I am today. And my focuses include severe weather, no surprise there, running weather models and correcting their errors, radar meteorology, and GIS, which is short for Geographic Information System. So before we get into the weather forecasting piece of this presentation, I figured I would start off with talking about the rise of billion-dollar disasters. So as you've seen in some of Haley's prior videos, our climate is certainly changing around and is changing around, unfortunately, to the more volatile part. So weather is becoming more volatile and is becoming more destructive. So the role and the importance of meteorologists and climate scientists is becoming even more important. There's no doubt about that. And since 2010, there have been 119 individual billion-dollar disasters in the United States. So this is a weather phenomena or a series of phenomena in one particular event that add up to $1 billion or more of damage. So the total cost of all of these disasters comes out to $802 billion. We, of course, account for inflation in this, which averages to $80 billion a year. Think about that. Weather, destructive weather, creates $80.2 billion of damage a year. It's impressive to think about the power of weather, but how more powerful weather has become compared to what we saw maybe 40 or 50 years ago. Now, there have been destructive events in those years, but the frequency of those events, one could argue, has certainly increased over time. Now, what are some notable events and how do they rank? Well, Sandy, for most people will remember this, third since 2010 with $73.5 billion worth of damage. So think about that. Sandy alone almost accounted for an entire year's worth of damage just from that one tropical cyclone, in this case extratropical. Hurricane Irene came in at 10th in 2011, just a year prior, and the Southeast super outbreak of severe weather, especially the tornado part in Alabama in 2011 as well, caused just over $10 billion of damage. So which weather phenomena are most prevalent in this entire breakdown? Severe thunderstorms, severe storms as a whole, no surprise, create just shy of 60% of the total makeup, followed by flooding at 15 and tropical cyclones at 10. So with that in mind, let's go to the introduction to weather forecasting. So let's take a second to recognize a few of the common statements that meteorologists today hear sometimes on a daily basis. You get paid to be wrong all the time. That's my personal favorite. Forecasting is so easy. I can look outside up into the sky and tell you what the weather will be for that day. Also misleading. And my phone app said blank. All three of these statements we hear more than you probably think we do. And all three statements lead me to this next question. So you think weather forecasting is easy? Well, it's inherently not simple. However, recent advances in our computing power and research and technology today have allowed us to make it very manageable compared to, say, 40 or even 50 years ago. So think about this. Weather forecasts are central to so many part of our daily lives and decisions. What clothing to wear. You're not going to wear a jacket if it's 85 degrees and humid outside. Outdoor activities, sports, or concerts. Severe weather can change those in an instant. NASCAR with rain. The races can't go on if the track is wet. Trading commodities. If we are going to have a super cold outbreak, obviously we're going to need to purchase more in the way of oil and natural gas. That will certainly reflect on the stock market. Trading of goods, freight, air, rail, superintendents needing to decide whether we're going to delay or postpone a school day based on a storm system coming in, how much snow falls, whether kids are going to or from school. Will that impact those travels? Whether we need to modify our plans ahead of severe weather, heat, wildfires in California. All of these things rely on one thing in particular, an accurate weather forecast. So, good meteorologists can assess a wealth of information, use their expertise and local knowledge, and correct errors to provide even more accurate forecasts with time. So, the first approach, the first method we're taught when we're in college learning about forecasting is one of the most common approaches that we use every single day, and that is the forecast funnel. Simply put, the meteorologist will look at the forecast starting with the big picture, so the synoptic or the mesoscale, rather the hemispheric scale, and then go down to the finer details, which we will call the mesoscale, and then all the way down to the local scale forecast, which you most care about. Will I see rain at X location? How warm will it be? How cold will it be at this specific location? What's the chance of severe thunderstorms or 12 inches of snow at this particular location? You get that from the mesoscale, the fine scale details. And it's important to note that each of these scales relate to each other, so it's important that we need to assess both, not just one or the other. So, of course, the next question is, a number of these scales look, and I've never heard of this before, how big are they? Well, we start with planetary and hemispheric. We're talking about global extent. So whether that be the continental United States, Europe, Asia, Africa, those make up the planetary and the hemispheric scale. So we're looking at waves of lows and high pressures and how those move along. We're talking about big circulations and how those move over days and weeks. Next, the synoptic scale. So we measure things using the metric system in meteorology. However, for those folks who maybe aren't as familiar with the metric system, of course, I included the conversion over to miles. So in this case, we're looking at 1,000 kilometers plus, which is 500 miles or more for a length. We're looking at a duration of days, and the types of weather we look at this particular scale and the synoptic scale will, of course, be areas of high and low pressure and how they move with time. Next, we go to the mesoscale, so 1 to 1,000 kilometers, which adds up to a half mile to 500 miles, potentially a little bit larger. And the duration of the weather phenomena in this scale usually last a couple of hours at most. And the types of weather we see, thunderstorms, tornadoes, and gust fronts, and how those interact, and of course, how long they last. So the first thing we need to do as a good meteorologist or as good meteorologists is obtain data globally, not just in one particular location, but globally, to get a detailed and accurate initial picture or state of the atmosphere. Our atmosphere is a fluid. And in order for us to get a good idea as to what's going on with the entire atmosphere, a highly movable and volatile fluid in some cases, we have to get a very detailed picture as best we can of the entire fluid across the entire globe. Think of it as like a bathtub of more than anything else. So these data help us assess how our atmosphere is behaving. We can assess and fix errors in our previous forecasts and previous model forecasts and make short-term adjustments to our forecasts we've made in the past. So the next big question will, of course, be how do we collect data to make a daily forecast? A few of these you've probably seen before, but a few of these you may not have known about. So we'll go through the main primary ways we collect data. Automated weather sensors and human observations, whether that be an observer saying I see a thunderstorm off in the distance, or an automated sensor telling me the temperature, the wind speed, and the dew point at the ground. Weather radar scanning into a thunderstorm or a snowstorm, telling us whether rain or hail or the intensity of those falling. Satellites give us an idea as to how much cloud cover currently exists over space, where the water vapor is most concentrated in the atmosphere, how deep, how high the clouds are, whether they have ice or just liquid droplets in them. Ships provide us crucial data over the most data sparse part of the globe, that is our oceans, believe it or not. So ships help us with that. And planes, to feed off of ships, give us another key piece of data sparse a region, or allow us to see into a data sparse region way up in the atmosphere. In the jet stream where these planes fly, we're able to collect basically key data from there. Now, also note that with COVID-19 going on, we've actually lost a lot of our air travel, and that's negatively impacted our weather forecasts, our forecast models, because we don't have as many planes flying around. Pretty interesting to think about. And the one that you've probably seen a lot, weather balloons, and collecting both temperature, humidity, and wind speed and direction from those. So we obtain all of our data in those 6 key components. There are, of course, a few more. And we get all this data into the WMO. They will have a strict process for both collecting, for any sort of correction to the data. And then they disseminate this data to a number of government agencies. So in the United States, we have the National Centers for Environment Prediction housed in NOAA, and they will collect the data. They will do any additional quality control that's needed, and then they will run it into their data assimilation systems and create model forecasts that we then, as end users, can take advantage of. We also can take advantage of that raw data as well. So some of the end users that will access this data include the National Weather Service, television, so us here on TV will use this data, private industry, and of course academia in both their research capacities and some operational components as well. So here are a few ways that we will look at the data. This is a look at GOES-16 there, so the satellite image on the left. We're looking at the presence of both ice and water droplets from space, and whether we see the onset of lightning based on a couple of other conditions there. We also can see lightning strikes from satellite. Impressive. We have NextRad, which is the next generation radar system run by the National Weather Service. We, of course, can look at radar imagery from that. The weather balloons imagery also provided by the Weather Service. We can plot that raw data and give us a very detailed look at both the temperature, the moisture, and the wind speeds, and of course derive other variables from those key pieces of data to tell us about the atmosphere at that launch point, at that moment. And we also have the automated sensors housed at a number of airports maintained by the FAA, and those allow us to see what's going on at the ground, in some cases every 5 minutes, which is really impressive. So our other ways we can look at data also include basically end users, which aggregate all these weather models and create model graphics for us to look at. So just a few examples, few of the many that are out there. WeatherBell, Pivotal Weather, the College of DuPage, we have weathermodels.com. All of these sources take in this data and create graphics that we can use to make our forecasts every single day. In addition, we have the meso-analysis, which is basically a near real-time weather system that allows us to see the current weather in the United States and how this looks both at the surface and above our heads, deeper into the atmosphere, collecting all this data and providing it into a crisp way that we can use this, and that is run by the Storm Prediction Center. So there are 4 basic forecasting techniques that meteorologists can take advantage of and use depending on the situation. So the first is the persistence method, which assumes the weather in the future will be the same as the current conditions. So the best time length, minutes to hours. An example of this would be, well, it's sunny now. It's going to be sunny in the future. Not really taking into account anything that could be changing. Well, one way that this could be used in parts is, I know that the high temperature today was 65 and it was sunny. If high pressure is remaining overhead tomorrow and there's very little change in the atmosphere, it's going to be sunny and it's likely going to be closer to 65. That is the example of a persistence forecast. Another one that's used a little more often is called a trend method, or the trend casting method, and that's based on the steady progression of a specific weather phenomenon, assuming that no other deviations to this occur. Best time length also minutes to hours. It's a short-term forecast, so we'll get into an example of that in just a moment. The analog method is basically pattern recognition. We can see a similar pattern and the conditions that it produced and look at our current atmospheric setup, compare it to a pattern that's happened in the past, and get an idea as to what the weather could be based on that pattern. We'll talk about that in just a moment as well. And the climatology method is a forecast created from the average of previous observed data, usually a 30-year period. So let's start with the trend method, or the trend casting method, and let's use an example. We'll use it in New York City and use the setup to basically make a trend forecast. So we know that there's a sharp cold front moving in out of the west here, out of the Great Lakes. So it's just east of Canton and Buffalo. This area of low pressure is starting to march into parts of Montreal and the province of Quebec in eastern Canada. It's hazy, it's hot, it's humid out ahead of this typical summertime pattern where it's very soupy, very hot outside, perfect ingredients for some pretty strong thunderstorms. So the sharp cold front is marching east at 40 miles per hour. The change behind the front means we're going to see a change in temperature of 20 degrees Fahrenheit, but downward. And the distance from New York City to where this front is positioned is 320 miles. So like I mentioned, there's warm air in place. We know our temperatures are close to 90 in some spots, and our dew points are close to 70 in a few of these locations as well. So the key question, what time will the front arrive, assuming that it is moving at 40 miles per hour at the steady state? What will the weather likely be ahead of the front and behind the front? So we know the front is 320 miles away. We know it's moving at 40 miles per hour. So in 8 hours time, we can expect, based on a steady trend forecast here, that it will be clearing New York City. Well, what would the weather be like ahead of it? We know it's hazy, hot, and humid. So we're going to expect sunshine to continue, it to continue to be humid. But as the front gets closer, we know that the thunderstorms will get closer as well. Now, will the thunderstorms survive? We know that thunderstorms are fueled by warm, moist air in part. So of course, if that remains in place, that certainly will allow storms in part to survive, assuming other conditions are met as well, and the front continues to march through. And will the forecast be behind it? Look up to the top left of the map there. We know it's less humid, it's cooler, and our temperature is dropping 20 degrees. So you can look at our temperatures, subtract 20 degrees. We're talking about 65 to 69 degrees as a total drop. So we'll end up in the upper 60s when all is said and done after the front passes. The analog method is an interesting one. And one of the patterns that we look for, it occurs in the majority of months throughout the year, only a few where it doesn't really pop up, is the PNA, or the Pacific North American pattern, and what that means for weather. So there are two phases to a pattern, in this case, this pattern. We'll get the positive phase and the negative phase. So in the western United States and in parts of Alaska, we have an upper level ridge, or an area of high pressure. It's sunny and dry, and we know that given that it's sunny and dry, it's going to be above average in terms of temperatures as well. In the east, upper level trough, an upper level area of low pressure, continues to spiral around. So we know that it's unsettled, it's stormy, it's dragging in cooler air from the north. So we know that they're going to be below average temps in this positive phase. In a negative phase, just the flip-flop of what the positive phase is, in the west, we know there's an area of low pressure, stormy, unsettled, below average temperatures. And in the east, high pressure builds in across the southeastern United States. That's going to pump in hot and humid air. It's sunny and dry, above average temperatures. That region now in turn will flip to the eastern United States. So the example you see on the right is actually a forecast from the ECMWF, and we're looking at what is actually a positive phase of the PNA, or the Pacific North American phase, or the pattern. And what we can see are basically high upper level heights across the western United States and low upper level heights across the eastern United States. So based on this forecast and this phase of the PNA, we can deduce the following things just from pattern recognition, just from seeing this before. It's going to be sunny and dry in Alaska and across the west coast and parts of the west coast, and towards the east, especially just out ahead of that area of low pressure, we're expecting unsettled conditions. It's going to be rainy, it's going to be wet, maybe we have some severe weather in the eastern United States. And we know that in addition to that, we are getting a lobe of colder air basically moving in out of Canada. We know that there are going to be below average temperatures regardless of season, with that air mass moving in, with that pattern in place. Now, any good forecaster will also use numerical weather prediction. So besides viewing the suite of surface and upper air observations, NWP is the backbone of our daily forecasting, day-to-day decision making. So what is numerical weather prediction? Basically, we're predicting how the variables of the atmosphere, pressure, temperature, winds, moisture, etc., will change in the future. Now, this utilizes a complex set of mathematical equations run under the hood of a lot of these models, or of a particular model, anyone you want to look at, which provide a simplified representation of the atmosphere. These models are fed an initial state of atmospheric conditions, as we discussed before, the initial snapshot of the atmosphere, which supercomputers then run and can solve quadrillions, think about that, quadrillions of calculations per second to give us a forecast into the future. The model then generates the forecast state of the atmosphere through time, which meteorologists will view spatially via a contour map, like you saw in a couple slides before, at individual points. Those are charts or meteograms, vertical profiles, etc. So there are three main types of numerical weather prediction that meteorologists can use on a day-to-day basis. First is deterministic. So it's a single forecast generated from a single set of equations and one initial picture of the atmosphere. Of the deterministic models, there are three subclasses of this computer guidance. The first will be global, obviously, as the name implies, the coverage is global, and the resolution. So the space in between grid points, or where the model is solving for an individual point. We'll talk about more about this in the next lesson. Ranges between 9 and 20 kilometers. The mesoscale is the next type. This spans from regions to perhaps a continent in coverage, is between a resolution of 1 and 12 kilometers, and some models now are run at the microscale, which are counties to a state level. These solve, or these predict or forecast or run using past events to model things like thunderstorms or tornadoes. Those are run at less than 1 kilometer in resolution. The next main class of a model is called the ensemble model, which is a single computer model creating multiple forecasts based on tweaking both the initial picture of the atmosphere, specific equations within some of these individual computer models, or a combination of both. We'll talk about ensemble models in the next lesson as well to give you an idea as to what that looks like. And the third is statistical. So this is guidance created by post-processing, or taking the initial guidance that's fed out and doing some adjustments to it after it's produced. So this can be deterministic and or ensemble guidance in order to further reduce error in models, which we called bias correction. So you have made it through the first On Cloud 9 lesson. Congrats. And now what's next? Let's go to lesson 2. What we'll be covering in this lesson is an entire expansion on numerical weather prediction. So I'll discuss what models are currently available for the public to access and where you can access them. We'll talk a little bit more about the different sites and what you can pull model data from. Show the limitations of weather models as a whole and break down core differences between global, mesoscale, and ensemble guidance. Each have a very different purpose, a very different way to utilize them, and excel in different scenarios. We'll dive deeper into statistical processing and highlight the advantage of implementing bias correction into daily forecasts. Answer a couple questions, such as, is it possible to run your own mesoscale model and generate forecasts? The short answer, yes. We'll talk about that. And what is a skillful extended forecast range? 5 days, 7 days, 10 days? How about 30 days? All those questions are incredibly good. They're great questions to ask, and we will get to all of those in lesson 2. So thank you so much for watching the first lesson of On Cloud 9. I'll see you back next time for an expansion into numerical weather prediction. Take care.